Hello, welcome back to the Vegetation Remote Sensing video series. My name is Marta Gebra, and in this video I'm going to show you some examples or that how remote sensing can support many aspects of fire management. So remote sensing can be used for pre-fire assessment of fire risk, real-time mapping of fire extent and movement, and also for post-fire analysis of burn extent, for example. So the information produced derived for remote sensing to assess the fire risk pertain to maps of fuel types, biomass, and fuel condition, as for example fuel moisture content. As for the real-time remote sensing, include maps of fire extent and temperature, observation of smoke plumes, and the dynamics of the lights, as well as the location of the fire fronts. Finally, immediately after a fire, it is important to assess the amount, degree, and location, as well as the condition of soil and vegetation resources. So the ultimate objective of looking at all these parameters is to produce maps of burn area, to estimate the emissions that has been released after a fire, also map burn severity and the regeneration of the vegetation. So let's start with the pre-fire risk assessment of wildfire. So the first application is to map fuel types. In this regard, we'll need to get information about the horizontal continuity of the fuel, the vertical distribution, the biomass loads, the surface conditions, and also the crown bulk density. This is because all these parameters will influence the way the fire will behave. You cannot retrieve all this information using any kind of sensors. For example, passive optical data can only provide you some information about the horizontal continuity or the fraction of cover, as we show in previous videos. But it will, as it doesn't penetrate the canopy, it will never give you information about these other properties. With LiDAR, however, as it has the capability to penetrate through the canopy, you can get quite accurate information about the vertical distribution of the fuels, and also the biomass loads and the crown bulk density. And also, if you are lucky, you can also get some information about the surface conditions, and as we will see later on. Radar is also quite a good sensor for mapping fuel types, but it is not as good as LiDAR, since it will never give you some information about crown bulk density. So this is an example of a crown point derived from LiDAR. Here you can see a picture of the same tree, where the distribution point crowd distribution is here, and you can see how you can get quite a good detail about the tree, and also some information about the understory. So as you can see, airborne LiDAR will never give you a lot of information about the understory, because there is always an occlusion effect, so the light beam cannot penetrate through all the canopy to pick up information about the soil or the surface fuels. So that's on the other hand, terrestrial LiDAR systems like the ZVT that you may see some examples in your tutorials. As the data is collected from the ground, you can get quite a detailed information about the surface fuels and the low parts of the trees. But you miss a bit of information about the the upper part of the canopy. So ideally, you will want to merge both technologies, both systems, airborne and CVT, to get a full representation of the canopy. So what can you do with the LiDAR points, clouds? So you can apply algorithms to retrieve a nice classification of the fuel array. Here, this is the result of our classifications following different rules that provides a nice map of different surface fuels. And from this, once you have the point cloud classified, you can get detailed information about the height of its fuel type, the width, and the volume, and many other properties that are of interest for forest fire management. The next application I'm going to talk about is the retrieval of fuel moisture content using remote sensing data. Again, I'm reiterating, you can map vegetation moisture content because the spectra from a dry and a wet green vegetation is very different. And this is especially true in the shortwave infrared, where the water absorption is happening. So there are several methodologies to map fuel moisture content using remote sensing data. The more typical and traditional methods have been based in empirical models calibrated with field observation of moisture content collected on the ground, and then satellite imagery recorded for the very same plots. But recently, radiative transfer models are playing an important role because they have demonstrated to be more physically based and robust. So as you have listened before in previous video series about remote radiative transfer modeling, these models assume that all the light that arrives to a leaf is either absorbed, transmitted, or reflected. So you can use these models in model in the way that from different input parameters you can get a simulated spectra, but you can invert these models, and from observed spectra you find which is the more similar simulated spectra and its corresponding input parameters, and you can use this to produce maps of fuel moisture content. The maps here present some examples of the use of radiative transfer models to derive fuel moisture content for Australia. As you can see, in January, there were low values of fuel moisture content in most of the temperate zones of Australia, and these areas gradually increased their fuel moisture content until reaching their maximums at the end of winter or beginning of spring around August, for example, and September. Afterwards, the fuel moisture content started to decrease until the end of summer, with the values were again the lowest. In the tropical areas, however, of the north of Australia, the tendency was the opposite. Higher values were observed as expected during the northern wet season, that is December to March, and then lower during the dry season from April to October. Yeah. The white areas in this region represent two values that were filtered out because of poor quality of the data. So how can these maps of vegetation moisture content of fuel types be used to estimate fire risk? Well, this is an example of the methodology followed in Spain in a project I participated when I was there, and the fire risk was defined by the probability of ignition and propagation, or the vulnerability. So this is how much a fire will impact on the landscape if it will occur. So as you can see, live fuel moisture content is a variable that affects both propagation and ignition, and the fuel types mainly affect propagation. So yeah, this is a quite complex and integrated way to assess fire risk assessment. So once you have these variables, obviously to be integrated in a single fire risk, you need to uniform the units. So, for example, fuel moisture content is in percentage of humidity of water content per dry mass. But if you want to convert it into probability of ignition, you need to have a physical property that allows you to do this. And this is mainly principally done using the concept of moisture of extinction. So here you can see that the moisture extinction is the value of fuel moisture content above which it is quite unlikely that a fire will happen, because the energy that needs to be released to ignite that fuel is too high. So there were linear functions that compared high values of fuel moisture content into low probability of ignition and low values into the highest probability on ignition. And this is an example from Spain. This is the region of Madrid, and you can see on your left the map of fuel moisture content and the corresponding probability of ignition. So the lowest values, as I previously explained, correspond to the highest probabilities of ignition, and the other way around. So this these maps can provide useful information for fire risk management assessment. So with this, I have finished with this short video, and you are welcome to click on the next video that will present some examples of near real-time assessment and observation of fires.